what I'm looking at here is the need to protect ourselves from causing interference or being vulnerable to interference. There's just an awful lot of people who say, "Oh, this is a noisy QTH," and an awful lot of them, unfortunately, end up slinking away from amateur radio with their heads down, which is very, very sad. Or else they go into something that doesn't involve transmitting and receiving, like building beacons. So I'm going to look at fairly simple, straightforward things you can do to hopefully reduce your noise levels on receive and avoid causing interference when you're transmitting, or reduce the risks. You can't totally protect yourself against the neighbour's piece of electronic rubbish, but you can protect yourself against pumping RF into the main supply that you share with them, for example. Right, so off we go. Things I'm going to cover include where does it come from, what can I do about it, and how to win both ways, because what you do from the transmit point of view is very likely to benefit you on the receive side as well. I'm going to be mainly talking about transmitting mostly because it's easier to explain that way, but from time to time I'll kind of turn things around and show how the same basic principles work with receiving as well. Basic principles are important here because EMC is an extremely messy subject. There are so many local factors that one important thing, if you're going to get anywhere, is to hang on tight to the basic principles and know that they will still be operating, although possibly in ways that are difficult to understand, but the laws of physics still keep going. Okay, but first of all, why hasn't this been in the handbooks for the past 50 years and so on? Why is this a new problem? And it's the 21st century perfect storm of everything going wrong together. The flood of electronic consumer goods, the amount of electronics all of us have in our homes has just exploded. Ofcom's weak enforcement policies, it has to be said, there's nothing to physically stop non-compliant equipment coming into the country. Certainly the failure all around to stem the flow of Chinese imports, which do not feel any strong compulsion to follow our regulations. And also a poor understanding of the technical problems, and this is top to bottom. It's not just our neighbours, it's not just Ofcom, although certainly there doesn't seem to be an awful lot of understanding within Ofcom, as distinct from Ofcom's engineers on the ground. And we have not had as much information in the amateur community as perhaps we could have. So what I'm trying to do is trying to avoid us being part of the problem of poor understanding. Right, so the result is your home is full of electronic devices that can easily cause interference to amateur radio on the receive side, easily be upset by your transmissions because they have poor immunity. And the same is true of your neighbours' houses and everybody down the street and across all of these islands. So that's the most important message. You can, if you promise not to give up on this, don't curl up into a ball, don't let your head drop. If you just promise to do that, you can go now and have some coffee. That's the most important message, is don't give up. There's a lot you can do, so this is an important chunk of self-training in the century we're living in now. Okay, where does it come from? faulty electronic installations and equipment, and I think we're well aware that even items of equipment that comply with the regulations can sometimes go wrong when they're in an installation. So installations and equipment have to be grouped together, but also an awful lot of non-compliant equipment that never did work properly, never could have worked properly because important things like mains filters are missing. What does it come from? How long have you got? There's just countless things here. At one time, the sort of classic exam question was about the faulty thermostat and the contacts tearing open, and these still exist. But they've been sunk underneath. Domestic appliances. At one time, a washing machine was a washing machine. Not anymore. It's a variable speed DC chopper drive. And the same applies to any kind of rotating machinery in the home. Computers are a problem because everything contains a switch mode power supply, and it isn't just the thing labeled computer. PCs, routers, network switches, printers, anything. Commercial electronics, just about everything we have in our homes has a commercial equivalent, and then there's more on top of that. Wide range of things. Security systems and lighting. I think we all know about the floodlights or the neighbours' floodlights flashing in Morse. LED lighting is a big growth area of interference. Again, it's power supplies. Road vehicles, of course, have turned into complex electrical systems, and that's not even thinking about the electrically driven ones, propelled ones. 11 kV, 33 kV transmission lines, still there, still as much subject to failures and gradual breakdown as ever. Electric railways, of course, although where we live now, they've forgotten what a railway is. Electric fences, we know about them. Those are not as bad as they used to be. The electronics that's in a modern day electric fence is, for the most part, a great advance over a sort of repurposed ignition coil out of a car. And then everything that I've just mentioned has its counterpart almost at high power in industrial equipment. And then whatever is coming along next, you just don't know what's going to arrive next door or accidentally arrive in your house. Okay, so let's get down to some basics and think about how it's created, how it gets into our receivers, how it gets out of our transmitters. How noise and interference are created. Overwhelmingly, it's about chopping up the main supply, which, as I'm sure you're well aware, is what switch mode power supplies, motor controllers, dimmers, all that kind of thing actually do. This is the classic textbook 50 hertz sine wave, which is actually what you get from a rotating generator. That gives you a very, very good sine wave. And that's how the mains used to be. I think you're probably also aware that a sine wave contains only one frequency component, its own fundamental, no harmonics, no distortion, no nothing. It's when the sine wave gets distorted that additional frequencies creep in. Like that. For example, that's a typical dimmer where it delays switching on until the applied voltage reaches that point, and then suddenly it jumps. runs the rest of the cycle and then switches off prematurely. So these verticals represent very rapid transitions, which mean that they are rich in harmonics. So the kind of interference you get, this is not going to carry to the edge of the room, but you know what this stuff sounds like. The interesting thing about that is the frequency, the dominant frequency that you hear there is not 50 hertz, it's 100, because those transitions happen twice in a cycle. So the sound it's a little bit more light-coloured than the fundamental 50 hertz, and you can also hear that there are other higher frequencies in there. Okay, the dimmer is turning things on and off very suddenly, and it's those sharp edges which are causing the trouble. The size of the step depends on the dimmer setting, but the same thing. You end up with almost only the sharp edges. So turning the dimmer down, for example, or turning the motor speed down, does not necessarily make the interference any weaker. Depends on a lot of other factors. The other effect of chopping up the mains supply is what you get in switch mode supplies, where you get flattening of the peaks. And again, distortion, again, sudden transitions where none should be, and introducing new components into the waveform that shouldn't be there. And these, in turn, depending what circuit they're in, can go on to cause trouble. How the peak flattening is, where that's coming from, is from switch mode power supplies, which are taking sudden gulps of current, predominantly just on the rise there towards the peak of the waveform, and then they stop drawing current. This again is basic stuff about rectifier and capacitor power supplies. That's the usual thing that appears in the exam syllabus, in all the handbooks and so on. In a switch mode power supply, there usually isn't a transformer. It's directly off the mains, but the same principle applies. Not everybody realizes that in a power supply like that, most of the time you're not drawing power from the mains. The equipment that's being powered is actually living off its reservoir capacitor until the time comes to take another gulp of current and top it up again. So, okay, you can see the rectified applied voltage is there, and that's the output voltage of the power supply. So it takes a gulp of current, and then the voltage drifts down until it meets the applied voltage coming up, and then it takes another gulp of current. And you can see that that's on the rising edge of the applied sine wave, and that is exactly what we see on the mains. So the problem, of course, is that we have now got dozens of that kind of power supply, rectifier, capacitor power supplies connected to the mains. Some of them are big. Our neighbours have got lots as well, and they are all gulping current all at the same time. So it's small wonder that, given the impedance of the mains supply, you can see the effects of that peak flattening, because they're all at it and they're all doing it at the same time. This this plot has got a superimposed Fourier transform spectrum showing the fundamental 50 hertz, which mercifully is still bigger than the rest of the rubbish, but all the low order harmonics. The low order harmonics are not going to do too much damage by themselves, but they do excite resonances in other parts of the circuit, like the parasitic inductance of transformers and so on, if there are transformers. And that's where the higher frequencies appear from, together with another bunch of higher frequencies due to storage time in rectifiers. When the rectifiers are switching on and off, you get another bunch of higher order harmonics. Okay. Yeah. The main problem is with unfiltered or inadequately filtered switch mode power supplies. Switch mode power supplies of themselves are not necessarily bad. It's just harder work to make them good. And one of the problems that we're well aware of course, is with non-compliant supplies coming in from the Far East, where the provision is made for the mains filter on the printed circuit board, and the samples that get tested for compliance have those in, and then somehow they mysteriously disappear. Yeah. Okay, and all of that interference, well, it goes forward into your equipment equally to the point it gets back into the local mains, and then by a route that I'm about to describe, it can get back into our receivers. So, right, this is a picture off the web of somebody's SDR looking at medium wave. You can see a couple of carriers, AM carriers there with their symmetrical sidebands. That's taken at an instant where their program material has a lot of bass in it and not much treble. That looks a little bit more like speech and its mirror image. That stripe is looking, that's the actual receiver passband. It's looking at a rather quiet chunk of spectrum, and the electronic S meter is showing about S3. You switch on the offending piece of equipment, and there goes your reception. The S meter's gone up to S9 of crud, and only the very strongest signals are audible. So that's the scale of the problem. It's also very typical of this kind of interference that it's broadband, but it's not level broadband. There are various things that you can only kind of explain afterwards that cause the severity to vary with frequency. Question is, how is it getting into your receiver? Mains is mains. Your receiver may even have a mains filter. The interference still gets in. How's it getting there? Through the aerial, predominantly. Through the mains a little bit. Through other attached cables, very possibly, because everything is interconnected now. It's no longer the case that your receiver is just connected to the aerial and the mains and nothing else. That's no longer true. By direct radiation into the receiver, no, not so much. I'll take a digression here, because it's a little bit of a red herring, and it's a useful digression through some basic principles. Okay, things we know, but don't necessarily always stitch together. Radiated signals in free space are electromagnetic fields. Okay, yep. Inside a receiver, radio signals are currents flowing along wires. Okay. And the thing that converts the one into the other is an antenna. That's it's a black box into which you put electromagnetic radiation, and out the other end you get currents on wires. Okay, that is universally true. So, if you're going to have direct radiation sort of sleeting into the receiver, if it's going to be converted into interference within the receiver, there needs to be an antenna within the receiver. And if it's going to be converted into strong interference, it needs to be an efficient antenna, which mostly isn't there, which is why I'm saying that radiation into the receiver is somewhat overrated, and predominantly interference gets into receivers along wires and cables, so we can then start to follow the current, which we can at least see in our mind's eye, and not bother too much about fields as such. So, through the aerial, through the mains, and the unfortunate fact of life is that the main supply is now, in RF terms, it's a sewer. It's heavily polluted. You do not connect to it, or you don't rely on anything to do with the mains as a sort of a source of RF quiet. That's rather crudely, but it particularly means if you connect something to mains earth, that is not a good thing usually, because if the live and neutral wires are polluted with interference, the earth wire runs right up between them. They're intimately connected. There are things like mains filters that connect them using capacitors. So you can say, for all practical purposes, that all three mains wires are equally polluted with interference, and so there's something to be careful of, something to be avoided, if possible. But the same solutions work for both receiving and transmitting. So if you do this clean up your shack thing, you can increase your chances of hearing weak signals and decrease the risks of causing interference. Decreasing interference risks is not something that you can easily quantify. Increasing chances of hearing weak signals, since I've been putting this stuff out, I've been getting a steady flow of, yes, it worked, my noise level has gone down. This is a lot quieter site than I thought it was. And the thing that put me onto this was a guy called W1HIS, who wrote up a blog a long time ago, it's still on the internet, of how he had this horribly noisy QTH, and by using absolutely heroic quantities of ferrite, you need to look that up. W1 Hotel India Sierra. The amount of ferrite in his house is just amazing. You can almost hear the sound of the ferrite truck turning up on a Monday morning and tipping on the driveway, but it doesn't need that much ferrite. So, how this works, I'll explain this in terms of transmit, and many of you will see where I've skated over one or two issues here, but we've got to crack on. Common mode RF current on the outside of the coax. Common mode current is something that is now creeping into the vocabulary, and people are beginning to think in terms of what it is, what the trouble is. I think you're aware that in general terms, what goes on inside coax is private from the outside world, but that the outside surface of the shield can act as a third conductor, which is in essence a fat wire, which can carry current, which means that the outside of the coax shield can be an antenna or part of an antenna in its own right. If you have something like a dipole without a balun in a typical asymmetrical, unbalanced environment, then you will have common mode current on the outside of the coax. The only question is how much. But it's there. Don't kid yourself, you ain't got it. The other thing we know is that currents don't just flow and then dead end. They've got to have somewhere to flow to, which is one of the things that we, I beg its pardon, one of the things that we hammer into students at a low level and then forget as time goes on, and we tend to forget it ourselves. So where's it going to flow to? The feed line's radiating because it's got RF current on it. At the other end of this lot, there's a connection to mains earth through a power supply, which may be inside the gear, may be outside. And that is where the current is going to flow. It's going to flow through the shack. In general terms, if everything is perfectly shielded, it will be flowing on the outside surface of all the shields which have no penetrations. That RF currents do flow on outside circuit surfaces, but they do get into places that where the shielding is broken. So you're going to have RF in the shack type problems if the unwanted current flowing through the shack is large enough. It's going to flow out into the mains, kind of trying to find earth in, to put it in crude terms, and you are injecting RF into the mains supply. So what can we do about it? First of all, the ferrite choke up at the feed point, which you can also call a balun, but to be honest, you're better off thinking of it, it's a choke. It's there to stop RF current flowing, taking a path that you don't want it to. That reduces the amount of current straight off. So the feed point is the best place to start, almost always. Possibly another choke where it enters the shack. Particularly if you've got a multi-band situation, you don't know where the current maxima are going to be, or it will take a lot of working out. So another choke at the entrance to the shack is probably a good idea. You may have begun to gather from this that bringing RF feeder other than coax into the shack is probably not a smart move, because you're greatly increasing the risk of these kinds of problems that we're talking about here being more severe. Okay, the other thing that you can do is to block the exit for that current by choking off the entire mains supply to the shack. And we'll come to the practical details of that later, but the effect of that is having essentially blocked both the entrance and the exit, things are going to be a lot better. There's going to be less RF in the shack. Correspondingly, the amount of common mode current on the outside of the feeder is going to reduce as well. At this point, I might add, I'll introduce the question of RF earth. Do you want to connect an earth point here which will only invite current to flow down? On most bands, you very well might not. RF earth is by no means a panacea. If you've got 10 meters of feeder, then on 40 meters you are actually creating. On 20 meters you're creating a situation where you're inviting current to flow down the outside of the feeder. On 40 meters, the situation's opposite, but if you work several bands, an RF earth can be a mixed blessing. Anyway, having done that much with possibly 3 chokes, the shack's clean, you're not injecting RF into the mains, and the situation's much better. Now let's flip it around, look at the receive situation. Interference from the mains supply in a sort of completely unprotected system can flow all the way back up the opposite way. The physics works both ways.
Of course it can.
Yep. Oh, I think I just heard a sack full of pennies drop there. Yeah, exactly. Yeah. As I said, it was easier to describe in terms of transmitting, but yep, the reverse works exactly the same. It gets into the shack, flows up the outside of the coax, and it gets in at the antenna feed point, at which point you're stuffed. It's indistinguishable from the signals that you are trying to receive. So the same solutions will work, and yeah, it's one thing to put this stuff out. It's quite another thing, and very satisfying to get the messages back saying, yeah, it actually did work. Thank goodness. Yeah, is there anybody called Mike German in the audience? Okay. I wondered if he might turn up. He's a medium wave, shortwave listener, and he latched onto this stuff. And to his great credit, he went the miles and did this stuff, and it worked for him. He's got his hobby back. He can hear medium wave DX now, and previously he had S9 noise. It took quite a lot of work and quite a lot of ferrite, but if anybody knows him, well, thank him from me, because I owe him thanks for having gone the miles, and sure enough, it worked once it was done properly. So you're blocking interference arriving, the shack is clean, and you're stopping QRM that had originated in the mains from getting in at the feed point. It's the same solutions, therefore, on both transmit and receive, and it's almost the same chokes. It's a choke. It's a thing to stop unwanted RF currents passing. So, yeah, those two chokes. That's this one and something rather similar to this. One's got coax going through it. One's got mains, but the same choke will work over the same frequency range. As a practical mains choke, I don't have a good picture of one of those, but the important thing there is that you've got a multi-way distribution board, which feeds everything in the shack from there, so that everything comes in through that one line which is choked. And I thought, am I going to bring one of these? And no, I'm not. Let me just point out what the essential bits are. That you want to have something that stops unwanted currents. In other words, everything but 50 hertz flowing along that line in either direction. I beg your pardon. Yeah. key points being all three mains wires, line neutral earth, must go through the choke, including the mains earth. Now, this is where a choke works, and most mains filters don't, because most mains filters take the earth connection onto the can, and it comes out. It comes out at the other end. It hasn't been anywhere. It hasn't been filtered. Mains filters are predominantly for other purposes. You used to be able to get 3-wire mains filters, but they're becoming rather rare now. And all a 3-wire mains filter is one that takes the earth lead inside, passes it through an RF choke, takes it out to the other end. There's a more elaborate mains filter that we're all familiar with for between line and neutral and connecting to earth. But you can make a better choke using ferrite. So everything in the shack must get its mains supply through that choke. Provided you're careful about how you route your connections and your PC is fed through the choke, you probably don't need one on the PC as well. And there must be no other paths to mains earth. That's tricky. That requires quite a lot of thought and a little bit of discipline, and we all know how shacks grow up, and the mess of wiring that just gets pushed over the back of the table. And if you're going to do this, then I would strongly recommend, I would strongly recommend knee pads. You are going to spend quite a lot of time on your knees, but by the time you've done it, you're going to have the shack sorted out in a way that's a number of other things are going to be working much better. I know mine has grown to the point now where I've got wires and cables running along a tray along the back of the table, and neither end goes to anywhere. And there are some that are only connected at one end, and I don't bother with the other end at all. So it's about time for me to get down on my knees again. All of this lines up well with what's needed for safety. That mains earth connections have got to be there, and you should never disconnect to mains earth, but you can choke it without interfering with anything to do with the current path or anything to do with installation safety. At the most, all a mains choke needs is a plastic box around the outside if you're going to be really fussy, or especially if you've stripped off the outer jacket of the mains cable in order to get more turns on a ferrite core, then you do need to put that back in a plastic box. And the other important safety thing is that everything ought to get its mains supply through one master switch. And if you route everything through one master distribution board, then you will achieve that automatically. By the way, I would not recommend that pattern of distribution board where you've got 2 rows of sockets, because there's numbers of sort of black wall wart plug-in power supplies that overhang, and you can't use the socket on the other row. The long strip type is much better. Okay, so right, making a mains choke. The reason I didn't bring one is that it's much easier. Was. Yeah, it's much easier to show you. The ferrite core I would recommend. It's on my website. the large Snap-on Fairlight Corporation from the USA, number 31 core. This has a 25 millimeter inside hole. You can get many turns of thick cable through that. You can get several turns of RG213 through that, for example. Other cores are available, although number 31 is particularly good for low frequencies. But the other important thing is that it's a snap-on bead, which means if you've got some slack in the cable, you can just wind a choke. And give it a try. And you can use the optician method. You know, is that better, worse, or about the same? That works. With that kind of choke, the other big advantage is you can use this outside the shack. You can try things in your neighbours' homes that are otherwise impossible, because people are no longer going to like you saying, "Oh yeah, I can try a toroid. Just allow me to cut your mains plug off, please." That's really no longer acceptable to them. I think it should be no longer acceptable to us, for the simple reason that there's a better way of doing it, a better engineering way of doing it, is to use a snap-on. They're slightly more expensive than toroids, but I always like to have one or two of these kicking around the house in case something turns up, and I literally would not leave the house for a special event station or anything like that without two or three of these coming with us in the box, because almost always something will be needed. And when amateur radio is on show, you only get one chance to get it right, and that really is important. So yeah, I recommend these very, very highly indeed. This particular bead, and the details are on my website. And about half a dozen turns through that will make a pretty good mains choke. Now, it may not be mains choke or indeed a choke in any of the other two locations. It may not be absolutely optimum, but you will find that a reasonably good choke will knock the problem on the head probably anyway, and it's only if you find yourself right on the edge of "I've almost cured it," then go back for another pass, do a bit more reading and think about how many turns, and could I make a better choke and engineer it a different way. But this will tell you if you've got the choke in the right place. Right, yeah, computers, difficult because of they've all got a pretty big switch mode power supply in, may need extra filtering for our requirements, or we may at least need to select a good one. Because of this requirement to pass all the leads through a choke and not leave any bypass sneak paths around it, it's sometimes difficult to share PCs for other uses, but there are plenty of old PCs which, if you strip out Microsoft Office and all the non-radio stuff, give them a really good registry and cache cleanup, then they're pretty good for radio use, unless you've got something really heavy duty like multiple channels of SDR. So radio PCs, a dedicated radio PC is a good thing to do. There are problems with sound cards and connections carrying low-level audio signals, sort of several feet across the shack. It's much easier with a dedicated radio PC. Also be aware that Ethernet cables can carry interference and also generate interference, but by linking up distant pieces of equipment, they all, the RF currents will divide in whatever ratio Ohm's law says, regardless of your wishes. That's one of the reasons, for example, why multi-operator transmitter sites these days tend to be moving towards Wi-Fi to network the individual sites, because otherwise Ethernet cables running across the site will tend to get enlisted into the general ground system, and it's asking for trouble.
Ethernet cables reasonably isolated by their transformers, though?
Not enough. Not for receive purposes. I've got sort of the office PC on one side of the room and the radio stuff on the other side of the room. Radio signals, particularly 6 meters, where there's an awful lot of clock spurs, cleaned up dramatically when instead of the reasonably well installed Ethernet cable, I hadn't just thrown it in, but instead of that, I broke that and used Wi-Fi just across the room, and it broke that connection, and things cleaned up really quite dramatically. The final thing I would say here is about bonding between various things. Metal cases, coax shields, and so on, they all, for RF good housekeeping, all need to be bonded together. And I'm talking here about for interference reasons, not for mains safety, because mains earths will be provided have been provided automatically wherever they are needed. But this is for RF and interference reasons. The key words here are bonded together. It's connecting things together so that all at the same RF potential sitting on the table and next to the table and so on. Please remember what I said here. I said bonded together. I did not say connected to Earth, because people wander away, and that bit about bonding things together tends to get overwritten. It defaults to the hardwired memory of, oh, if I connect it to Earth, everything is okay. No, it's about connecting things together. Incidentally, they will also be earthed. For RF bonding, low inductance, short, wide, direct conductors. Speeding up here, the old-fashioned star grounding with a single earth point won't work for RF, because you've got multiple long thin wires are not going to leave the things at the ends of those wires at the same RF potential. So you want something like that. Wide strips of metal, I've normally used strips of PC board, which give a low inductance, and if it's double-sided board, it's about 6 inches wide. That is actually, I can't remember the exact number, but it's more square millimeters of conductor area than you think. But that's only important at low frequencies. What's important at high frequencies is the width of the thing, which makes it low inductance. And then you bond that strip at one place to where the mains comes out of the filtered distribution board.
You've literally got a printed circuit board going around the tabletop, have you?
Yeah. And one advantage of that, it's lower inductance. You can buy copper bus bars, but that is completely misunderstanding the problem, because the inductance is higher. You don't, for RF purposes, you don't need the copper in the middle, which is what you've actually paid for by weight. And it's kind of something to do with some lingering idea about lightning protection. And if you've got heavy copper bus bars deep inside your house, in the shack along the back of the table, you have misunderstood the problems of lightning. All all that stuff needs to be outside. Okay, one final practical example of tying together a transceiver, a power supply, and a PC as represented by a sound card. The RF bonding picks up on those wing nut connections, which most of us never use. They're there, but most of us never use them. In the case, if you use PC board, then with a big soldering iron, you can dab down a piece of braid so that it just sort of pops straight up and goes straight on. You can also use plug and socket connections. The audio in and out of the rig goes to the sound card and indeed to the rest of the PC, not forgetting that the PC is earthed, has a mains earth connection. So the PC's main supply kind of is paralleled by the RF bonding, and to a large extent it's shorted out by the much lower impedance path in parallel. Okay, then you connect up the DC, and within the rig, the DC negative is connected to the frame of the rig in a way that the designer of the equipment has hopefully thought about and sorted out, but you always find a negative supply connection on the back of the rig, and you must connect to that and not to the frame of the rig for your DC return. That is fairly obvious. What's less obvious is that inside the power supply, it mustn't be earthed at that point. Many are, and you can solve that problem by going inside, snipping the earth connection, putting something like a 1K resistor in between the negative and the frame, the mains earth, so that there's something to tie it down. It's not completely floating, but it needs not to be earthed, as opposed to it doesn't need to be earthed. There needs not to be an earth connection in the power supply, and then everything I think will be well. So I'll just leave you with four big things to remember. Use the ferrite chokes. Use the proper ferrite chokes. That is, don't just sort of hand-wavingly say, "Oh, I tried a ferrite bead and it didn't work." Come on, please. Try harder. The whole station mains choke is tremendously effective. I had a lot of trouble down south, which was just cleared up by doing that. I don't have the same problem where I am now, but also bond the equipment together, at the very least by having it close together and tying it together with braid of sort of RG213 size braid or bigger. It crops up, you find it from various places. And the final thing to remember is that the benefits are on both transmit and receive. So it's worth cleaning up the shack to reduce your interference risks, and you can also get big improvements in receiving weak signals.